Hey everybody, welcome back to our Materials Informatics playlist. Today we talk about Gaussian processes. So this builds off of our last video on naive Bayes theorem. Now we're going to extend that to Gaussian process. So I'll be the first to admit that these are kind of tricky to understand. I myself really found them a little bit hard first time I looked at them, but there is a great website. Check it out here. It's distill.pub. This was back in 2019, where they have this really great visual exploration of Gaussian processes. This is awesome. It allows you to explore the different kernel functions. It shows you how the function updates in real time as you add data. And it's explained really well. So highly, highly recommend this to check it out. That said, why should we care about this? Why didn't we just stick with naive Bayes or any of our other machine learning models? Maybe a good way to elaborate why these are so powerful is to ask, how would you fit this function, right? You have X and Y axes here, and you have a collection of data. How would you fit that, right? You could imagine all sorts of different ways. Maybe you try a linear fit or some sort of polynomial fit, right? The actual true function, it could actually look very different if you have limited data scenarios, and it'd be hard to figure that out. But Gaussian process model actually does a pretty good job of finding trends in pretty complicated data, and I'll explain how it does in a moment. Okay, so let's go back to naive Bayes for a moment. Naive Bayes had us making our prediction for something conditioned on something else based off of multiplying our prior probability by likelihoods of our features. Okay, so it looked like this expression here, right? This conditional probability was equal to some other probability times a series of other conditional probabilities based off of features that we know about the material. But that approach could really be generalized to any function, right? This conditional probability could be just equal to some function g that takes into account inputs x, our features. Okay, so that could be a linear approach, like you see here, where now our conditional probability is now going to be a linear expression with respect to what we do know, x, that's the given, right? And then our beta, which are the parameters of this model, right? And if it's a linear model, then it's like beta 0 plus x1 times beta 1 plus x2 times beta 2, right? That would be a linear regression. In this case, this is parametric. The data is not normally distributed, and there's a linear relationship between the variables, right? So that would be one function that you could use. But you could also do, say, logistic regression. Maybe you're trying to do a classification problem. And you could do a gazillion other models, right? There's not just one. There's so many different ones you could use. So what we're going to introduce here is, instead of relying on linear or nonlinear approaches to fit our data, we are going to rely on Gaussians. So you might be thinking, like I did when I first learned about this, like, why on earth would you use Gaussians? Those have a super specific shape, right? Here you see 4 different Gaussians with 4, means and their standard deviations listed. And they have these sort of different shapes. So while they can have different shapes here, the overall shapes are all still Gaussian looking. So how's it going to fit data like we saw here, right? Well, I'll show you how it does it, okay? First off, we have to do some definitions. When we talk about Gaussian probability distributions, these are always defined by a mean, right? The middle of that curve, and standard deviation. So here you see an example of a Gaussian distribution, a normal distribution, centered around 0, so the mean is 0, and then you have a standard deviation of 1, right? Okay, that's how we're going to go about defining things. And this is obviously a Gaussian distribution in one dimension, but you could have it in higher dimensions than this, right? You can have a multivariate Gaussian distribution, right? So here on the left, you now see a picture where you have x and y dimensions, and you're pulling from now, it's a normal distribution, but it's distributed across 2 different axes, right? Your x and your y axes, so it's higher dimensional than just one. Now, in this case, this is the example of a naive Bayes approach, where the different parameters, x and y, are independent of one another, right? There's no correlation. So in math terms, we would write this, that the mean of both of these in the x and y axes is still centered around 0. And then you have this covariance matrix, which tells you how they vary with themselves and with one another, right? So here you're seeing that they have there's the diagonal terms, which shows you that how they vary with themselves, and then the off diagonal terms, which shows you how they vary with the other different features present. And in this case, those off diagonal terms are set to 0. And that's exactly the scenario we have with our naive Bayes. Naive Bayes assumed that all the features were independent, that they weren't related to one another. But as we sort of saw, that's not going to be the case. Very often in materials informatics, the different features they're going to use, electronegativity, the size of the ions, the number of electrons, right? Some of these, there might be actual correlations there. And if they're correlated, then these off-diagonal terms can't just be set to zero, which is why we're now going to introduce Gaussian processes as an extension of naive Bayes, where these off-diagonal terms are not just zero. Like, for example, this one. What if your x and y have a general correlation? As x increases, y increases, right? Now your off-diagonal terms are set to something else, and you can see that it went from being a perfect sort of circular covariance to now some sort of elongated ellipsoid, okay? So that allows us to have high dimensional space where we can control the relationship between our higher dimensions, right? Our variables, okay? Mathematically, it looks like this. Forgive the messiness, right? But you've got your probability of some sort of outcomes like y1 and y2 given a mean and your covariance matrix. That's that capital sigma, right? So this then would be equal to you're drawing from a normal where you know what the means are, and then here's your covariance matrix. So that's the mathy explanation of this. Now, there's a reason why we like Gaussians, though. They do two really cool things. First off, they are easy to marginalize. When we marginalize, we remove all or parts of the covariance matrix except for what we want to keep. So for example, let's say you wanted to drop this y2 term. You're only going to predict the y1. To do that, all we do have to do is drop these three terms in the covariance matrix. It's very simple to do. And we drop mu2 as well. And then they're also easy to condition, which is if you are given the value of one value in our multivariate normal distribution, it allows us to calculate what the other value would be, right? So for example, you can see mathematically what that comes out to, what the probability of x given y would be. Using this expression up here, we're actually able to calculate it. Not too bad. You do need to have this conditional mean term, this conditional covariance term, but those are pretty easy to calculate. So that's the mathematical description. I think it's easier to think about this in terms of graphs. What does this allow us to do? Well, think about this. Marginalization allows us to extract individual distributions. So you had this higher order distribution, which was two dimensions, x and y. Well, marginalization allows us to select, say, a value of x, maybe it's the one at x equals 0, and extract what the distribution along the y would be. So this is an example using 0 for x and using the 0.5 where we're able to extract out what this distribution would look like, right? And you can do that for any value of x, right? Here it's taken at 1 for that same distribution. But here's what it looks like with a different, right? With a different covariance matrix. That same value of x equals 1 gets a different response. We get that from conditioning. So conditioning tells us how different random variables relate with one another, okay? So we're going to use marginalization and conditioning to construct functions. How do we do that? Okay, this process is called Gaussian process, right? And it's really a collection of infinitely many Gaussians, okay? So let's start by taking a single value along the x-axis. We'll say x equals 2, right? We could use marginalization to construct a Gaussian, right? So there's some distribution. Now, we can draw from that distribution. So because it's a normal distribution, we can draw from it and we get a point, right? Maybe the point is exactly at its center, but because it's a distribution, maybe it's at some other point, right? In fact, it could be any of these points, but it has to correspond to the underlying distribution. So we're going to pull one of those. And the idea is that this was all done at an x value of x equals 2, but you could also do it at x equals 5 and at all these other different values, right? And in this case, they all have the same marginalization, right? But that doesn't have to be the case. Even if they're the same function, underlying function, because you're drawing them randomly at each one of these different values, they're going to be a little bit unique every time you draw them because you draw randomly from the normal distribution. Therefore, if you picked along every value of x and you drew randomly from the distribution, most of the time you'd expect it to be near 0, right? Because that's where the overall probability existed. But you could have different values that sort of move around like this. This is now what we're going to do. This is an example of drawing from marginalized Gaussians to produce a single function. Now this function no longer looks like a Gaussian, curve because we drew from infinitely many, obeying their distributions at each one of those, okay? If you drew it as, multiple times, here we're doing 5 different draws from these marginalized Gaussians, and we're able to produce 5 different functions, right? And in fact, if you drew it infinitely many times, the overall response starts to look like, yeah, you guessed it, a Gaussian, right? Because you're drawing from Gaussians at every single point in this case, in this scenario. So the overall distribution looks like a Gaussian, okay? So this ability to sample many, many times is we're going to use it in the Gaussian process, okay? Next, we have conditioning. Conditioning is going to restrict neighboring points to some subset of values, right? So let's say we have an actual honest to God data point at x equals 2, which means that here at whatever this is, 2.5 or whatever, here's the distribution that marginalization gave us. And so technically it can be any value along this distribution. Conditioning restricts that subset. It says, okay, it can't just be any value. Because it's near to this value data point that we have, we're going to restrict it. Maybe it can only be values within some range, right? That process is called conditioning, okay? So we are now able to draw functions that are conditioned on observable data. So here's 5 draws of functions where we know that a data point at x equal 2 has this value. So all of your functions have to collapse and equal that value. By the way, that value can be a specific value or can have some uncertainty. More on that in a moment, okay? So then the next question is like, okay, if that point is valuable, how valuable is it to values beyond it, right? So if your x equals 3, do you still have to be really close to it or can you be kind of far? That comes from what's called the length scale parameter, which is simply going to tell us how much should the point here be dictated by the point that we already know. How much influence should this have on the points near to it? And so this correlation length scale is a tunable parameter that we can explore to try and figure out ways to make our Gaussian process fit the data that we're actually observing. So that's a tunable parameter, hyperparameter. Okay, so here you see 3 examples. So here you see 3 examples, L equals 0.5, 1.5, and 5. You can see that if it's a really short length scale, then the Gaussian processes are able to do much more variation. In medium and towards long, you see that they're forcing it to obey. They're learning from this one data point they had, and they're not allowed to vary quite as much. And then the variance parameter, well, this controls the spread of the possible functions. So now think of if the length scale compresses it in the x direction, this is now compressing it a little bit in the y direction. If you have a very small variance, then all these functions have to be a little bit close to one another. Medium and large allows them to vary significantly more. So this is another hyperparameter that you could imagine using to make your data fit some sort of crazy curve, okay? Overall, the generic expression for how we define these Gaussian processes is using a mean and a covariance function. The most common way to define the mean is to use a constant. You just like set it to 0. Like that's what you've been seeing in the previous examples. But it doesn't have to be. It doesn't even have to be a constant. It could be like a linear changing one, for example. And then the k is your covariance function, and that again is going to define how 2 points in space are correlated. So here's one very popular example. This is the RBF kernel. If you go back to our support vector machine videos, you saw this before, right? This tells you how 2 points in your data set are correlated one with another by passing them through this function, okay? Which again has a length scale parameter. In terms of the covariance matrix, it looks like this, and this again comes from that awesome Distill publication, which shows you really cool visualizations of what these covariance matrices look like. But the point is that you can try lots of different mean functions and covariance functions, right? If your overall Gaussian process is defined by your choice of these functions, and there's lots of different values, then you can get lots of different shapes. Like here's an example of one covariance matrix. And just changing, I think, the scaling parameter on this one, you're able to change it quite a bit. Like take a look at this one. Like it went from being much more smooth to having much more jagged ability to change just with a very small change. Or this one, here's a pretty dramatic change. Here they're using actually like, it looks like a sinusoidal kernel function, right? So it's an oscillating value. And maybe your data, it makes sense to have that sort of oscillating functionality to it, that periodicity. And here's the types of curves that could be drawn from that one. Or here's one where it's a combination, right? It's got a radial basis function, it looks like, and it's being added to that a linear term. So you can see that it's able to, when it's nearby, it has strong correlation with it, and then it's able to blow up and get quite large, okay? And the website, that Distill page, has lots of really cool tools. Like here they have RBF, here they have periodic, here they have linear, and you can explore what variance and the length parameter will do. If there's periodicity, if there's an offset, you can actually see what it will make it look like, which is pretty rad. So the pro of this is that you can make these Gaussian processes fit many, many types of data, right? There will be a downside, of course, right? So here's another one. Here's an exponential quadratic, really common. This looks like the RBF, right? Here's one. This is the matern 3-2, another popular covariance function. You've got two terms, right? The 3 and the squared, I assume, is where the 3-2 is coming from. You've got a length scale parameter plus some sort of term to scale roughness. Here's the cosine variation one. In this process of picking the right one, there's this kernel hyperparameters. Learning how to fit them correctly is a bit of an art. Hopefully your algorithm, your optimizer can learn how to do it, but you do have some choices. Like here you can see where the length scale was too small. If the dashed line is the overall curve that you're trying to learn, the length scale was too small. And as it got longer, they realized, oh, now we're able to capture the actual length scale, right? There's less incorrect variance with new data points. This can also be done by learning from derivatives a little bit more effectively. It's a nice paper on this by Derringer in Chemical Reviews back in 2021. And then the mean function, I said before, oftentimes, the simplest is just to either use the average, right? Use the average as the mean function, or to set it to 0, so like a constant or 0. But it doesn't have to be. It can be linear. Maybe it is linearly changing plus some variation due to whatever your kernel function is. But these are all learnable things that you can try and learn. Here's an example of where the mean function was set to 0. So when you have data points, based off of the distance function, eventually it's going to go back to the whatever you set for your mean function, which in this case was 0. So in the absence of real data points, it will collapse down to this 0 value. And then it has another data point, will go up to that, but eventually it's going to try and collapse back down. And that's by them choosing 0 for their mean function. They could have chosen another value or some linear function or anything else. Okay, so how do you actually use Gaussian processes to predict something? Well, if we go back to our Bayes formula in our previous video, we know that the conditional probability is equal to this sum of all these different, conditional probabilities for each of our data points. We're trying to take and predict these things based off of what we know about our systems. And previously we said that looks like, okay, you've got Gaussian data, you're going to multiply that by a Gaussian prior. Okay, and then when you fit the model, you're really just learning what the correct functions should be for your kernel and your mean hyperparameters. When we actually go about making predictions, the posterior predicted distribution looks like this, right? So you've got some new data point that you're trying to predict, given the data points that you know, right? These y values. That's going to be the integral of these two terms, where the first one takes into account your aleatoric uncertainty, which is just noise in the data itself. And the second one takes into account your epistemic uncertainty, which is our unknowns, right? The prediction is simply then going to be drawing from the distributions with our new mu and our new covariance matrices that we've learned by training the model, which is pretty awesome, okay? So this allows us inherently in this process to have confidence intervals and predictions that come out of our distribution statistics. Because again, because we're drawing from normal distributions for our predictions where you have a mean and you have a variation, well, you can always deviate, right? And so the standard deviation tells you how much you'd expect it to. That allows us to put confidence bands. So in these diagrams, when you see like actual data points, that's where they know the model is, fit to the data. But out here where they have no data, these regions of, pink here, for example, that's typically plus or minus 1 or 2 standard deviations. It depends on how you're choosing to plot it. But it gives you an idea, like it's pretty unlikely that there's a data point outside of that distribution, but it's possible. And everything's possible, right? Because you're drawing these from infinite many distributions. And the idea is that if you draw a bunch of them, which are these light gray lines, that you should be learning the breadth of types of Gaussians that could fit your data. But you could always have an outlier and then you have to refit your data. And that's one of the strengths of Gaussian processes, that it works so well with active learning. You get a new data point that broke it. Well, great. You can refit your entire data set, all of your Gaussians, to find that new data point, and you've learned something. Okay. So here's some examples, right? Here's 3 attempts at posteriors where you've got the solid colored lines are us trying to learn that distribution with a bunch of actual data, right? Here's 100 attempts, and then they do it again, but now they are able to add prediction noise. So they're increasing that uncertainty, the aleatoric uncertainty, so they're able to make it fit. Okay. So that said, before we wrap up, we should say a few things about the limitations of Gaussian processes. These are incredibly popular. They're called Kriging. They go by a lot of different names, and they're really popular. But they do have some limitations. First off, extrapolation can go really poorly with these things, although it does depend on your length scale, right? If your length scale is large, maybe it allows you to force your models to fit near your data, points near your data, to sort of comply with what your model's expecting. But otherwise, as you go outside of it, look like your uncertainty sort of blows up. Your predictions might not go well if you're trying to do extrapolation with Gaussian process. They are not sparse. They use the whole sample/feature information to perform their predictions. Okay, and because of that, they lose efficiency in high dimensional space, which unfortunately for Gaussian process really means that if you've got more than say like a dozen or a few dozen features, these things become really problematic. They sort of fall apart. And then another, I think, real problem is that you have so many options to choose with your kernel, right? Your mean and your covariance function, that it's sometimes hard to determine what was the right one that you should use. And that's not straightforward to figure out. It involves typically trying a lot of things, which always leads to this notion of you're just going to abandon it at some point. You'll never know if you've done it correctly. You're just going to abandon it and say, hope it's good enough. Okay, so we're going to take that concept of Gaussian process, and now we're going to turn it loose to actually do something with the materials, which is the best example of it is doing Bayesian optimization. So check it out in our next video.